So, welcome back to this next lecture on plant-wide control fundamentals. Today we are going to look at more deeply the snowball effect, which has consequences on control structure synthesis. So, we will analyze a simple process for the snowball effect and then see where that takes us. So, the process that we're going to look at is again like a toy process, and it's going to be a very simple process. So, what we have is a CSTR with cooling. You got fresh A coming in, it mixes with recycle A, and the reaction A goes to B, occurs in the reactor. Conversion is 30, 40, 50% single pass conversion, and so the reactor effluent has product B as well as significant amount of unreacted A, and the reactor effluent is distilled in a column, and you take out unreacted A up the top, which is recycled back, and product B down the bottoms. So this is our process. We've got P, the product rate, the composition of the product is XBP, its purity, the recycle rate is R, its composition is so this is A recycle. So this is the very simple process, and we are going to look at this process. Let me draw this process, a slightly smaller version of this process, because we're going to do some derivations. So that's my process. ये क्या हुआ? कहाँ चला गया? So we'll say FA, and this is product P, XB, P, and this is recycle, XA, recycle. A goes to B, occurs in this reactor. Temperature is fixed, reactor volume is also fixed. So reaction rate is standard first order elementary kinetics. So K times XA is the reaction rate. XA is the mole fraction in the reactor. So now let's do some analysis. And what we are interested in is as the production rate P is changed, we want to find out how does the recycle rate R change with production rate P. We also want to find how does the sensitivity of the recycle rate to production rate P vary with the production rate P. These are the two things that we want to find out. And in order to do so, let's do a little bit of analysis. So if you look at the overall material balance, the amount of B generated in the reactor must be equal to the amount of B being withdrawn as the bottom of the column. So we have the amount of B generated in the reactor, that's KXAV. This must be equal to bottoms rate P times the amount of B in it, that is XB in P. So the left hand side is generation rate of B in the reactor, and the right hand side is the amount of B being withdrawn from the process. No B is entering in the fresh feed, so we are assuming that the fresh A is pure A, okay, for the time being. Okay, that's number one. So this is overall material balance. Now if you look at the column, if you look at a balance on the column, then you'll see that XA, I should write it here, reactor A is equal to mole fraction of A leaving the reactor is going to be equal to the amount of A leaving the column divided by the total flow leaving the column, because the total flow leaving the column is the total flow into the column, which is the reactor effluent stream. Okay, so we will have R times XAR plus P times XAP divided by R plus P. That's the mole fraction of the A in the reactor. And now if I substitute XA into the overall material balance, what I will get is, you start substituting, what you will get is then K times V times XA, and XA is R times XAR plus P times XAP. This must be is equal to R plus P times P times XBP. And now we will take all the R terms together on one side and everything else on the other side. So what we will have then is KV times XA recycle minus PXBP, this times R is equal to what, man? Is equal to P square X BP minus KV times P times X A in the product. That's what we get. Now what we do is we say, okay, R is equal to P square times X BP minus KV times P X A P divided by KV times XAR minus P times XPP. So this is the recycle rate expression that we get. Now this business of KV, it's easier to replace KV with something more tangible. And what I would like to point out to you is that, imagine that the recycle rate is increasing, recycle rate is tending to infinity. If the recycle rate tends to infinity, then the composition of the reactor effluent will be the same as the recycle composition, because you add a little bit of A and a little bit of it reacts, doesn't really matter. The composition of the reactor effluent will then be XAR. So if you apply this in your reactor material balance, if the recycle rate is infinity, then your mole fraction of A in the reactor is as large as can be, and it would be the same as the mole fraction of A in the recycle stream, and therefore the production of B in the reactor is as large as possible when the recycle rate is infinity. Yeah, and in that condition recycle rate will go to infinity when this chap goes to 0, which is essentially saying that the overall material balance left hand side minus right hand side should go to 0, and this goes to 0. When this goes to 0, recycle rate goes to infinity. When recycle rate goes to infinity, your production is as large as possible. So we will call this production P max, and as we call this P max, what we then get is, if you substitute, if we say that KVXAR minus P max XBP is equal to 0, because that's when recycle rate will go to infinity, and what that then does, it gives us KV is equal to P max times XBP divided by XAR. And now what I want you to do is replace this KV and this KV with what? With P max XBP divided by XAR. Here too we will get P max XBP divided by XAR. This XAR cancels. You can see this guy and this guy cancels. Also XBP cancels out. Okay, so now what you're left with is, oh man, so if you try and simplify this, maybe I should just delete a few things here. Maybe I should just so what we get is, Control Shift 3, what we get is R is equal to P square minus P max P XAP by XAR divided by P max minus P. This is a much simpler and neater expression, and we can simplify things further by saying that divide numerator and denominator by P max of the right hand side, and then divide both sides by P max. So what you will get is, and maybe I should use a different color here because this is going to be of consequence. Maybe this is of no consequence again, so I'll keep it black only. So what you will get then is R by P max is equal to P by P max whole square minus P by P max into, maybe I should erase a few more things. Yeah, maybe I should erase this. Make some space here. Divided by, okay, sorry, x a p by x a r, and divide this by 1 minus P by P max. And let us call this guy small r, and let us call this guy small p, and then what we get is, and maybe this is of consequence, what we then get is r is equal to well, what we then get is r is equal to p square minus p x a p divided by x a r divided by 1 minus p. What this equation is showing is that as your production approaches P max, R, or scaled recycle rate, goes to infinity. Yeah. So recycle blows up as production is increased. That's what this equation is showing. So we have gotten this. Now to get dr by dp, we'll differentiate both sides. So now what I'll do is delete pretty much everything other than that. And so from this overall material balance and the column material balance, we have been able to get R. And now if you differentiate and solve, differentiate both sides of this equation, what you should get then is dr by dp is equal to 1 over 1 minus p times 2p minus 2p minus, okay, sorry, minus x a p by x a r divided by 1 minus p, and then we'll have plus p square minus p x a p by x a r. Take this guy, and then the differential of the other guy will be 1 over 1 minus p whole square, and then differentiation of that guy, so there will be a negative sign here, and then the differential of what is in the bracket will be negative, so this will again become positive. So I think this is what we get. And now if I take 1 minus p square common, what I'll get is equal to 1 minus p whole square has been taken as common, and then what I'll get is 2p into 2p minus xap by xar this guy multiplied by 1 minus p plus p square minus p x a p by x a r. And now let's start seeing what all will cancel out. So plus pxa p by xar, so and this is minus pxa, so this guy, okay, so maybe I cancelled it too quickly, yeah. So if you do the needful there, I think what you'll get is dr by dp is equal to 1 minus p whole square minus 2p square plus p square will be minus p square. Okay, so that's actually 2p minus p square minus xap by xar. So the rest of the stuff is not so relevant. What we were looking for, those two equations we have been able to derive. And by the way, dr by dp is the same as dr by dp because you multiply and divide by p max, both numerator and denominator, this is the same thing. So this is what we wanted, so we've gotten this too. So these two things are now we have been able to obtain. So I will just summarize this in the next slide. So what we did, was we took this process, we had the overall material balance, we also had the column material balance which gave us the reactor mole fraction in terms of R, P and XAR and XAP, and from this, combining both the top equations, we were able to get recycle rate in terms of P, kV and mole fractions. Now as R goes to recycle rate goes to infinity, P goes to P max, so if you put the denominator to 0, you get kV is equal to P max xb by xbp by xar, and if this is substituted into the R equation, what you get is this guy, and if you replace R by P max and P by P max as with R, small r and small p respectively, that's the equation that you get, that gives the variation of the scaled recycle rate with the scaled production rate. And if you differentiate both sides and do the necessary algebra, we are also able to get the sensitivity of the recycle rate to production rate. So we get R and dr by dp. Okay, now that we have done this, let's assume, by the way, if you take a look at this, The recycle rate blows up as P tends to 1. It should also be obvious that the sensitivity of recycle rate to the product rate, that is dr by dp, it blows up faster because the denominator is a quadratic, whereas in the relationship of r and p, the denominator is linear in 1 minus p. So as p tends to p max, that is small p tends to 1, recycle rate blows up. dr by dp also blows up, but dr by dp blows up faster. Now to get an appreciation of how fast or how severe is this blowing up, let's take an example where the product is assumed to be pure. So XAP is 0. Okay, so if XAP is 0, this term goes to 0 and this term also goes to 0. Yeah. And now, so actually only pure P needs to be assumed, but that's okay. We have also assumed that the recycle is pure. So now what I did was I just varied the scaled production rate from small to large. It cannot go beyond 1. And from this equation we were able to get these values, and from this equation we were able to get these values. Okay, and now let's just appreciate what's going on. See, when production rate is 90% of maximum, we're looking at this chap, recycle rate is about 8 times production rate. But look at the sensitivity. I make a 1% change in P, and the change in recycle rate, you know this guy is 99%. That's extreme sensitivity. And this sensitivity is quite extreme even if recycle and product rates are the same. That means P is equal to R 0.5, and you can see that here dr by dp is 3. That means if I make a 1% change in production rate, recycle rate will change by 3%. That's a gain of 3. Okay, and this is when the process is operating at 50% of max, or process is designed for 50% of maximum achievable production. Okay, so you can see that the sensitivity of recycle, even though the product rate and the recycle rate are the same, the sensitivity is still 3. Yeah, only when product rate is about a third of the maximum achievable product rate for that reactor volume are we getting a sensitivity of about 1. That means you make a 1% change in P, R changes by 1%. So what this shows is that A, recycle blows up as product rate increases. B, the rate of change of recycle with production rate is much more sensitive. It blows up much faster. And this is evident, or this will be clearly evident in these figures that I made in Excel. It took me a long time to figure out how to make figures in Excel, but these have turned out to be reasonably okay. So the first figure on top is variation of recycle rate R versus P, and you can see that at 95% of maximum production, where are we? We are probably around 18. This is around 18. Here it's of the order of 100, and we are not even at 95%. At 90% we are 99. Yeah, so this is at 90% of maximum production we are 99. Okay, so the sensitivity dr by dp, or the percentage change in recycle per unit change in production rate, this is extremely sensitive to the oh this axis is wrong. This is scaled production rate. This is scaled production rate P. Okay, so as production rate is increased, dr by dp increases and it blows up much faster than r itself. Okay, now what are the consequences? Well, this is where, as I was speaking in the last lecture, high sensitivity of recycle rate to production rates. You make a small change in production, recycle sees a large change. You want to increase production by 5%. That seems like a small change, but let us say your nominal steady state is here, so your gain is of the order of 5. So you want to increase the production rate by 5%. Recycle rate increases 25 to 30%. Distillation columns are designed at the nominal steady state to have a boil up that is 80% of the flooding boil up, or the vapor superficial velocity through the column is 80% of the flooding vapor velocity. What that means is the vapor velocity can the boil up can be increased 25% before the column floods. Well, this process, if you want to increase the production by a mere 5%, the column will flood, or will get very close to the flooding limit. And that is the problem with the snowball effect. The recycle shows large swings, or the recycle is highly sensitive to production rate changes, and a small change in production will cause a very large swing in the recycle rate. And because of those large swings, some unit in the recycle loop reaches its maximum or minimum capacity limit, and then you have operational issues, and that is the consequence of the snowball effect. Okay, control shift. Okay, now what do we do? Now we go to the next slide. How do we go to the next slide? Alt tab. So when production rate, the high sensitivity of recycle rate to the feed rate, this is called the snowball effect, and the snowballing region corresponds to that high slope region. I've also seen processes where the relationship between recycle rate and fresh feed, and by the way, in both these, where the relationship between recycle rate and fresh feed rate is not monotonic, it shows, it shows a turning point. That's the dashed curve right there. In both these cases, note that there are no feasible steady states beyond the maximum production rate. There is a maximum production rate, and there are no feasible steady states beyond the maximum production rate. Now imagine a situation where you are setting production by adjusting a fresh feed. So operator has, let us say your base case is over here, the operator has set production here, and now you see this curve, these curves are not static. These curves are not static, they move. They move because, for example, the catalyst deactivates. If the catalyst deactivates, this curve will go to the left hand side. it will move to the left hand side. As it moves to the left hand side, do you see that this production rate, which was previously just feasible, has now become infeasible because it is now beyond the new maximum. The new maximum has reduced. This is the problem with fixing the fresh feed rate. So, fixing the fresh feed rate of a recycled component is not a good idea. And this is because you can always be very close to the maximum, and then as the maximum limit reduces because of degradation of equipment, you become infeasible, and then you are eating more than what you can digest. Your process is eating more than what it can digest, and because it is not digesting what is being put in, the undigested component simply builds up in the recycle loop. So you have the possibility of overfeeding induced instability. What is the solution to this? Well, just turn the curve over. Instead of taking this as the independent variable, take this as the independent variable. If you take this as the independent variable, no matter what you specify it as, there is a steady state solution. Yeah, and because there is always a steady state solution, now the operator is confident no matter what I specify my recycle rate as, I will end up at a steady state. In this case, the operator is not confident. The operator is not confident. Well, this is the am I too close to the maximum? And if I specify it to be here, maybe I just reach a steady state. If I specify it to be just a little more, if I specify it to be here, now I am above, now I am in the infeasible region, and what then happens is, you are essentially eating then more than you can digest, and you will fill up your system, your recycle loop will fill up with the undigested component. And in this case, the operator will then be very, very conservative. He'll say, well, I'll set it here and I'll never go to that region where you don't know where the cliff is. This is like falling off a cliff. You keep walking, and suddenly there's nothing there. You just fall off the cliff. Yeah. So specifying this guy is not a good idea. Specifying this guy is a good idea. So fixing the fresh feed rate of a recycled component is not a good idea because there is always the possibility of overfeeding induced instability. There are also very sound dynamic reasons for not doing it. We'll talk about that maybe in the next lecture. Control implications. Well, I think I talked about it already. So this is a conventional control system where you are fixing the production rate at a fresh feed, and then we've seen this before. We've got level controllers and pressure controllers and temperature controllers. This is a standard conventional control system, and in this case, small change in the fresh feed rate will cause a very large change in the recycle rate, and because of that, the operator will be very conservative. He will not want to go towards the maximum because that maximum can shift and you can have overfeeding induced instability, and so he will always be operating reasonably far away from the maximum possible, and therefore you have what you call large throughput derating, as I spoke in the last lecture. So recycle loop or recycle flow will show large swings, and therefore you get large throughput derating. Now let's look at the other control system, which is just a subtle shift. Instead of having it like this, you're having it like this. So what you're doing is you're holding the total flow to the reactor fixed and bringing in the fresh feed, adjusting the fresh feed so that the total flow to the reactor remains fixed. So this is a fast enough control loop, as fast as flow control, and in this case all the other loops are the same. All the other loops are the same as before. And in this case, like I spoke in the last lecture, the action of the flow controller, the throughput manipulator, is such that it transforms variability out of the recycle loop. And in this case, because you are, if you're looking at recycle versus fresh feed or production rate, either is fine. Do you see that this curve actually looks like this? And this is your maximum production, and no matter what you specify your recycle rate as, you are guaranteed a solution. Alternatively, if you had the curve like this, even then, no matter what you specify your recycle rate as, you are still guaranteed a solution. And that gives the operator the confidence, look, I can adjust my recycle rate set point, and this is recycle rate in the sense of a flow in the recycle loop, inside the recycle loop. So the total flow to the reactor is a flow inside the recycle loop. Okay, so now the operator will have the confidence, I can adjust this to whatever value I want, and there is no issue of falling off the cliff. Guaranteed the process will settle down at a steady state as long as the tuning has been done properly. And therefore it is because of this confidence that now the operator can get close to now in this case you can operate at the maximum. Operator can adjust the set point and still operate at the maximum. Yeah. So in this case, you don't see large swings in the recycle rate because you're holding the recycle rate fixed, and therefore you're able to operate at the maximum or very close to the maximum. You're able to operate the process close to the, for example, flooding limit of the column. Now this this flexibility is almost always there. You will always have a process in which you're putting in a feed and you're taking out a product and things are getting recycled in the process. That's the figure that is shown right there. This is the conventional way of doing things, where you fix the fresh feed rate and flows in the recycle loop are under level control, pressure control, and product is also taken out under level control, for example, or pressure control if it's a gas product. So that's what I am indicating by IC, inventory control, whether it is liquid inventory, gas inventory, maybe solid inventory. So your recycle rate is governed by inventory controllers, and your product withdrawal rate is also governed by inventory control. So now you're fixing the fresh feed rate. The fresh feed rate is fixed, and because you've got the level controllers in the recycle loop that are setting the recycle, so fresh feed is fixed. In this case, feed rate is fixed, recycle rate, because of inventory controller, because recycle rate is being manipulated by level controllers or pressure controllers, depending on whether it's a gas recycle loop or a liquid recycle loop. Recycle rate is going all over the place. If you look at this, transforms variability into the recycle loop. You can always choose a control system structure where instead of fixing the fresh feed, you fix the recycle flow. That's what you do. And now the fresh feed must be brought under inventory control, and the product is of course withdrawn under inventory control. In this case, what happens is, now the recycle rate is fixed and the fresh feed rate is going all over the place. Because the recycle rate is fixed, all the equipment inside the recycle loop see relatively calm flows, relatively fixed flows, and therefore they are not disturbed. You get smooth process operation, and typically this fresh feed is coming from a big tank. There's a big supply tank. If you see a refinery, you'll see all these tank farms. They are storing products, intermediate products, and supplying this plant, that plant, and the variability of the flow here, what will that cause? That will cause this level to go up or down a little bit. which is the purpose why those big tanks were put in place to begin with, to dampen out flow variability. So wherever and whenever possible, this is what should be done. This should be avoided. This can always be done if you've got a big tank supplying the raw materials to your plant. If that is not the case and your plant is supposed to process whatever is being given to it, in that case there is no option. This is the control system that you are supposed to work with, and that's the control system that you will work with then. But wherever and whenever it's an option, it's always a good idea to go this way rather than this way. Okay, so that's the point, the major point of what I was trying to make in this lecture. And by the way, this control structure right here, the bottom control structure, this transforms variability out of the recycle loop. You see, this inventory controller is transforming variability out of the recycle loop, yeah. So again, the transformation of variability perspective is very useful in figuring out how to structure your control system. Continuing, it's time to summarize. So what we have discussed or shown for that simple process is that recycle rate typically exhibits high sensitivity to production rate changes. This is the snowball effect. And if we have our throughput manipulator at the fresh feed to such a process, it will result in large swings in the recycle rate, thus disturbing the entire plant. It may also result in overfeeding induced instability, where you are eating more than you can digest and the undigested material simply builds up in the recycle loop. When the throughput manipulator location is flexible, it is a good idea to fix a flow inside the recycle loop. This is also called Liebman's rule. And to bring in the fresh feeds as makeup streams under inventory control. The fixed flow rate inside the recycle loop should be used as a throughput manipulator. If you want to increase or decrease production, you use the fixed flow rate, the recycle flow rate that you're fixing as the throughput manipulator. What I mean to say is, for example, in this case, if you want to increase production, what do? You basically start cranking up this set point. If you crank up this set point, this flow is to be increased. In order to increase this flow, you start bringing in more feed. Yeah, that's number one. There is a subtle thing that I want you to note. You see, if you see the steady state relationship, and we'll say F versus this flow, let us call this the total flow T. The F versus T relationship is going to be something like this, and this is the limit, the maximum, F max. Let us say I'm operating at this steady state. Maybe it should be, yeah, here's the steady state. Now, whether the control structure is independently setting F or independently setting T, whether the throughput manipulator is the fresh feed or whether the throughput manipulator is T, please note, if I have to go from F to F plus delta F, so this is my current production. If I have to go from F to F plus delta F, I'll have to end up at this steady state, and at this steady state, you see this? So the steady state that you're looking at is the same. It's just that when you're specifying T, you will change T from here to here, and then the production rate would have increased from here to here. If you want to still increase production rate, Now you will have to make a larger change in T for the same amount of change in production, and then you'll end up there. If you still want to increase production, you make the same amount of change again, and now you will end up here, and the production rate is this. On the other hand, if I am specifying F, if I crank up production and bring it here, oh, now I have become overfeed. Now I am overfeeding. So you see the benefit of specifying T is this guarantee of ending up at a steady state and never exceeding that maximum limit. However, this should not be confused. You are always ending up at a steady state. If you are ending up at a steady state, when you were here, like this, like this, the point is whether you are changing T, whether you are changing F. If the production rate, if the production rate is the same, that means you are at the same steady state, whether you are operating using the conventional control structure or using T as the throughput manipulator. That's the subtle point that I wanted you to distinguish. The only thing or the major thing that holding T, using T as the throughput manipulator brings is that you are guaranteed that you'll end up at a steady state, but there is non-linearity. What's the non-linearity? When you are at low production amount, this amount of change brings about this amount of change in production. When you are in high production rate region, this amount of change brings in a, for the same amount of production rate change, you need to change the recycle rate much more. That's the non-linearity. So the non-linearity is there in T. Yeah. Okay, so that's the point that I wanted to make, in the sense that you are ending up at the same steady state. It's just that when you're specifying F, you can always specify F to be too high, and at that too high F, there is no steady state. You're overfeeding. The overfed component will keep accumulating in the recycle loop, and that is a big issue. Ultimately, the column will flood, and then the operator will have to intervene and make sure all the liquid that is stuck in the column is somehow drained, and then restart the process. Nobody likes to do that. Okay. All right, so that's that. I think I'll end the lecture for today. Yeah. Thank you so much for your attention. And what is that alt tab? कहाँ गया यार? कहाँ गया भाई? Okay, there it is. We will go to active presenter. Oh, this lecture has also been a long one. So thank you again. Happy viewing.